Montreal's very own Guillaume Lajoie. So another excellent example of the former primacy of Seattle and neurodynamics before he moved here and made Montreal the new place, apparently. And so Guillaume did his PhD at the University of Washington with Eric Shea Brown and probably many other people in collaboration. And now is a professor here at the University of Montreal and a core academic member of Mila, where he leads a research group doing a range of things at the intersection of neuroscience and AI, from responsible AI development to neurotheory to neurointerfaces to just AI for AI's sake and everything in between. So I'm excited to hear what he'll tell us about today on his plasticity-less credit assignment.
Thank you. Thank you for the kind introduction. And I cannot, pretend to have moved the needle on the already existing expertise of dynamics and neuroscience in Montreal. I'm just glad to actually strengthen bridges between both Seattle and Montreal, if anything. I think these two communities are great. It's the first time I'm presenting at Maine, actually, and I'm quite excited about it. I've toyed with what to present. I was considering presenting some results on BCIs and learning, but it would have been a tough act to follow. I mean, Kayvon's talk was so nice that I actually decided to take a step back and talk about a question that I think I'm very passionate about, and that takes on, I think, quite a big picture view of intelligence, right? And so in the spirit of Maine, which is the intersection of AI and neuroscience, I think we ought to, allow ourselves to really ask questions that are both relevant to neuroscience and AI, and not just like poach ideas from one towards the other or tools from one to another. And poach is a violent word. I didn't mean to say it like this. But I do think that there's value, especially now, to think about the common principles that might be universal surrounding intelligence. Not just AI, not just neuroscience and biological intelligence, but principles of intelligence. And I say this now because we have the situation where multiple architectures, multiple approaches are leading to performance that are kind of comparable and sometimes surpass each other. I'm thinking about, for example, large language models that rely on architectures that are farther and farther from the brain, but that perform equally well and even better at some tasks. But it's actually a rich opportunity to ask about what are the underlying principles in these both artificial systems and biological systems, but that might support the sort of like high order cognitive tasks that we see AI systems come up with today, and we know biological system can. So I want to, I know it might be pretentious and a little bit pompous, but I want to approach the questions from that pretty big point of view, if you'll allow me. And I think this is a safe space to do this. So I'd like to talk about a particular topic, which is the idea of credit assignment without plasticity. And Alex set up that question pretty well with his question to Kayvon. Like, what happens if you think about learning but without changing any weights in your system, right? And so this is a principle that's explored actively in neuroscience these days. We've heard about fast learning from Laura's talk earlier today, where it's shown that you can reuse learned motifs just by modulating the inputs to your network. There's a slew of different type of contexts in which this is relevant to think about credit assignment learning without necessarily thinking about synaptic plasticity. And furthermore, I think this is underlying a lot of the recent boom in large language models and AI in general, right? So if you think about all of these things like prompt engineering, chain of thought, fine-tuning, zero-shot learning in LLMs and sequence models, these are also examples of things that do not require any weight changes, right? But at the same time, we do use deep learning to train these big models, to train weights, to get to these things. So there ought to be a relationship between these dynamic ways of doing credit assignment and parametric ways to do credit assignment, and this is what I want to discuss today. And so most of what I'll talk about, fits under the category of what can be called in-context learning. So this is learning that happens based on input to a system. So by ways of introduction, I want to give you a little bit of an example of to make this a little bit more real. This is a cute example that I've borrowed actually from Blaise Aguirre-Arcas, who is in the Google team where Alex is from as well. And so here's the question, right? We asked the LLM, have you ever heard of equi-iso-antonyms? So this is a word I've made up that has some semantic meaning, right? But I've made sure that it doesn't exist, right? And then the first thing is that the system is trying to bullshit, right? Like, oh, I'm trying to piece together the pieces of this word, blah, blah, blah. And then I reply, I said, no, that's not really what it is. Actually, I'm providing a definition of what I mean by equi-iso-antonym. And by what I mean it designates pairs of words that have the same number of letters but opposite meanings. And I've kind of made my best to verify that there's no other word that means that, right? Like, that's kind of a made-up concept. And you can ask the system to give examples of equi-iso-antonyms. And lo and behold, the system kind of does well, right? You'll notice that it kind of doesn't enforce the number of letters pretty strictly at the end of this list, so you can tune it a bit more, and without too much tuning, the system can do the task. Now, if you pause and think about this task, there's no changes of weights that happen here. This was never in its training set. Everything has been done in context, right? I give example, I give instructions, and a task has been acquired, right? Learning has happened. So this is an example of in-context learning that takes on instructions or examples and comes up with a way to do credit assignment. And so, underneath the hood, the main objective that's been used to train these big large language models is essentially sequence prediction, right? If you think about a context as a series of words, then the job of a large language model is precisely just to predict the next likely token or word based on the context, right? So it's a probabilistic model. I'm giving you the probability of the next word. Here, after, the brain is in D, you'd have a large probability distribution, large mass on the word head, right? And the interesting part about in-context learning is that it's essentially quite a general setup to do general supervised learning inference, right? You can think about introducing task instructions or example in context and ask the answer to be the next likely predicted token. So here's an example of such a packaging of a supervised learning task. Let's think about regression, right? I have a bunch of examples, pairs of points, x and y's, and I'd like to come up with a nice model of what might predict any other query, any other x. I want to have the next likely y given all of this data set, right? This training set. So you might want to come up with an estimate, an inference of this model. Now you can repackage this as providing this training data set as examples in context, right? All of these pairs, x and y's, I can give them in context, and then give a token x star as a query, and then whatever the prediction now becomes the most likely y, right? So this is an example in ways you can repackage any supervised learning task in context. Now, if you think about what happens when you do this, well, there's two steps to it. First of all, you need to train a general predictive model, right? And this is where you use credit assignment in weights, right? You use deep learning to train a predictive model to do what's the next likely token when you do a prediction. And then once you have this model, there's a second type of learning that can happen, and this is, the in-context part, which, in this particular case, you can think about training a large system on the entire internet, right, or all of everything that's been written. This is that little globe here that I'm qualifying that model G with. But if you think about the in-context model that comes out of predicting condition on context, then you're conditioning not only on this entirely trained models, but also in the context that's provided, right? So, and this happens only via activations, right? So you take a pre-trained model, you condition on context, and then you get a new model in which you can put anything here and get an answer to it, right? So it's a new way to do, it's another way to do machine learning in some sense, okay? And so a lot of time you'll see that's the dichotomy in the literature as in-weight learning versus in-activations or in-context learning. And the big question I want to ask now is, how does this like plasticity and activity-driven learning combine to support higher order learning, right? And how might this be useful in different contexts? Okay, and I think there's two ingredients to this question, right? The first of which is circuit mechanisms. What is it about neural networks that actually might enable to do this at scale and really flexibly? And the second is, what are the learning mechanisms that lead you to have these types of principle being possible? I want to spend most of the time today talking about the second point, but I'll just mention that the circuit mechanisms part, I think, is under quite heavy study in neuroscience, right? We've heard about the talk from Laura earlier that looks at these reuse of neural motifs. There's all kinds of other examples here, also from Matt earlier today. But and some of the work coming out of my group is looking into at the basic level, what type of guarantees can you get if you're just driving neural networks? So we have a paper out by Ezekiel, I don't know if he's in the room here, where we show universal function approximation theorems for random networks in which the only thing that can are learned are essentially constant inputs to the network. So we're excited to do like headway on the circuit level question, but today I'd like to really focus on the second part, which is the learning mechanisms that might lead to this dichotomy of credit assignment mechanisms. And so I want to tell you a story that from a paper here that was led by Eric Elmosnino, who's sitting in the room right here, and all these awesome folks here, and together with Danya Sridhar, who's also a professor at University of Montreal and at Mila. And the take-home message here, the spoilers, is that essentially I want to argue that sequence prediction finds actually the simplest models better than optimization in general, and that the simplest models generalize best. And this might be a good way to think about evolutionary pressures of having brains that both use plasticity and in-context learning. So that's where I'm going with this. Okay, so in order to make that argument, we'll use kind of esoteric-ish quantities that have been developed by a good old Kolmogorov, right? So I want to introduce briefly the concept of Kolmogorov complexity of an object. So this is if you think about it, the measurement of the Kolmogorov complexity of a data set or of a string is essentially how hard is it to describe it in the most compact way possible. So for example, if you think about the string here, 42, 42, 42, 42, you can think about the complexity of that string as the length of the shortest program that can output that string. For example, the shortest program is just repeat 42 12 times. As opposed to a string that's completely random, you have no other choice but to hard code the string itself in the program. So in this particular example, it's clear that the Kolmogorov complexity of string A is much lower than string B. Now, computing Kolmogorov complexity in general is pretty hard. You can define it very nicely, but you'd have to search over all possible programming languages and come up with an infimum over this. But you'll see we don't need to compute it in specific ways. That's going to be quite useful. The second thing I'd like to mention is that you can think about Kolmogorov complexity. You can manipulate that quantity pretty much like probabilities, right? So you can think about conditional Kolmogorov complexity of two variables, k, x, and y, and you can decompose this joint complexity as the conditional complexity of y given x plus the complexity of x, and so on and so forth. And you can also think about the complexity of models, of functions, of pretty much anything that you can express via a programming language or a Turing-complete language, right? And one thing that comes out of thinking about the complexity of a function, a relation between x and y, is that you can think about the complexity of the function that equally explains the data between two functions, for example. So you can think about, say, function A that explains all the data points here, function B that explains the same data points. But arguably, and this is an argument referred to as Occam's razor, and that's applied to in science in general, is the most simple model is generally the best, right? So simple models generalize better. So it's desirable then to get models or functions that not only explain your data, but that are simple enough such that they will generalize better. Okay, so what we're after here is Occam's razor in inference, right? You want models that are compact, i.e. they have low Kolmogorov complexity. And to illustrate this is, I like this example a lot, like if you think about celestial prediction over the time of humanity, right? Like you can think about early Babylonians that kept tracks like lunar phase records in which they could kind of predict by looking at the past. And then fast forward a bit more, you have Kepler that had kind of a hybrid of between having these tables of celestial movement and a few laws, but nothing was kind of set in stone. And fast forward a little bit more to Newton that came up with universal laws of gravitation that actually generalize much better than anything that came before, right? So arguably, Newton's laws are the most compact laws that explain observations, and they're actually the ones that generalize much better, right? So that's the idea behind Occam's razor here, and that's the idea that we want, right? We want models that have low complexity. Okay, so let's do a little bit of math here, and I promise it's worth it, so please stay with me, okay? Let's start with a data set, right, that comes from IID from some distribution, so a bunch of points, x1 to xn. Now, one thing that we can compute is the Kolmogorov complexity of a data set given a model of the distribution that it came from. Right? And that's easy. That's essentially just the negative log likelihood of that model probability distribution. Right? This is precisely the loss that's used to train predictive models, sequence models like LLMs. What you want is you want to minimize the negative log likelihood of the model. Okay? So this turns out to be exactly that conditional component, conditional complexity of a data set given a model. And for those of you who are more familiar with Shannon information theory, this is exactly similar. It's actually the same thing as the Shannon information under the Huffman code hypothesis. Okay. Now let's come back to our decomposition of this joint Kolmogorov complexity between a data set D and a model P, and then we can decompose it this way, right? It's one part is the conditional complexity of D given P plus the complexity of P, which is the thing we want to minimize, if you remember. Now, we have this part here in the middle. That's only the negative not log likelihood. So then what I'll show you is that we can actually estimate this left-hand side and therefore get a handle on this guy here, which is very hard to compute. Okay? All right, so stay with me on this. Now let me introduce one more object that we'll need. Suppose that we have an optimizer or a learner. So this is a function that takes a data set and that spits out the optimal parameters for a model class that best explain that data set. One example of T is gradient descent, right? Given a data set, do gradient descent until you converge, spit out the parameters of that convergence. This gives you this would be the answer that is given by T of D. Okay, so it's argument of this. Now, given an optimizer, one way to estimate the joint Kolmogorov complexity of a data set and a model that's given by that optimizer is to compute something that's called the frequential length. So let me walk you through this, but it's dead simple, okay? What I'll do is, for my data set, I'll just pick one point, train my model on that one point, and then predict one other point. The prediction is going to be garbage, right? I've just trained the model on a single point, so I get pretty bad log likelihood of that model. Now let me add that point in, retrain the model on 2 points, and predict the third one, and do this over and over again, right? So this is what's called the frequential curve. Obviously, the last point here is the model that's trained on the entire data set and predicting 1 point, right? But if you sum all of these intermediate points, essentially it can be shown, and this is a nice piece of work here from Blier and Olivier, that this is essentially an estimate for the joint Kolmogorov complexity of the data set and the model itself. Okay? So if you do this kind of ratcheting of training, you train over and over again on longer and longer parts of your data set, you can estimate the joint complexity of the data set. Okay, so now let's say this is given an optimizer T. But now let's parameterize my optimizer T, and let's say I want to do as best as I want in minimizing that entire frequential curve, right? So I'll parameterize my optimizer T. Now, you can't think of it as SGD anymore. It's just some model that takes on a data set and that spits out another model, right, that explains the data, right? And what we'd like to do is to minimize the frequential curve length. In other words, I want to minimize the joint complexity of a data set and the model that comes out of that learner, of that optimizer. So desideratas for T here, T should be fast to evaluate, right? Because I need to evaluate it on ever-growing data set. I want to optimize it so it should be gradient friendly, and it should be expressive enough to have a large class of optimizers. Now, it turns out that this is precisely what autoregressive sequence prediction does, okay? So if you think about it, in context, what a big sequence model does is it predicts the next token, i.e. it predicts the log likelihood of my next token in my sequence, given what's come before, right? So the argument here is that I'd like you to picture this optimizer as being your sequence model. The parameters of my optimizers are actually the weights in a sequence model, whereas the parameters of the model that's spit out by this optimizer are actually this model that is held in context in the activations of the network itself. Okay? Now, the idea here is that the optimizing part of a large sequence model is actually minimizing the learner that actually takes a data set in context and spits out a model that's in context, right? So if we take this perspective and we run through the argument, we get the following thing, okay? I start with the point of view that I want to train my sequence model with parameters phi, using deep learning, using gradient descent, to minimize the frequential length curve. This is the same thing as doing some autoregressive sequence prediction, right? Because you do this on ever-increasing sequences of tokens. I remind you that this is exactly the same thing as computing the joint Kolmogorov complexity of a data set and a model that comes out of this optimizer. Now, if we remember, we can unpack this joint complexity into a conditional complexity here and the complexity of the model, right? And this thing is precisely the loss that you would train a model on in general, right? So this is the negative log likelihood. It's the loss of, given an entire data set, predict a new point that you give you your generative model. So what I want to argue here is that sequence prediction trains for both minimizing the log likelihood of a model and the model complexity itself. If I were to remove this part, then you're back to standard meta-learning approaches, i.e. you take a bunch of different data sets and you try to meta-learn an optimizer or like a learner that fits the best models for these data sets. But if you do this with the autoregressive sequence prediction, what happens, and that's the take-home message, is that you end up jointly minimizing both the task and model complexity, right? So you both explain the data and you get for free the most compact models that you can hope for, okay? So this is a normative account on why sequence model actually learn quite well in context, right? And I want to give you a few examples as to why this might be the case, right? So this is an interesting paradigm shift in the sense that given a data set, you might not want to use optimizers, right? You might want to use general predictors that train up, like essentially act as optimizers on the fly, if you have enough meta-learning ability. Okay, simple experiments. We compare these two ways of learning on a couple of toy tasks. Sinusoidal regression, which is basically regression on a bunch of points that come from sums of sinusoidals. What we can see here is that in low data regime, if you train transformers in this particular case to take a sequence of points as examples in context and predict a new token. In low data regime, if you train on frequential objectives, i.e. next token prediction as a sequence, autoregressive sequence, you get way better generalization when you just see a few points. This is compared to similar architectures on which you just train on something that's equivalent to just train risk, which is the objective without having that frequential flavor. And you can compare it to training on the same number of data sets, but just with standard stochastic gradient descent. And what you can see is that although in high data regimes, all models do pretty well, right? And that's perhaps not surprising for regression tasks. In low data regime, leveraging sequence model as optimal optimizers actually gives you in-context models that are quite generalizable, okay? And the same is true for another toy task, Mastermind. I don't know if you remember this game where you have to like guess the number of orders of tokens and the colors and so on and so forth. I won't go too much in details because I want to show you some other thing before time runs out. But the same idea happens, right? Like if you train on frequential objectives, what you get from the same data is better, more generalizable models. Okay. This is somewhat architecture agnostic. You can do this with transformers. You can do this with sequence models that come from state space models, which is essentially glorified RNNs. It doesn't really matter. As soon as you can train a predictive model to do some next token prediction and you can package a task that is supervised, you can show that you have these advantages in low data regimes with in-context learning. So the fact that all these curves look the same is a good thing. In Mastermind, that's true to a certain extent because in some cases, some architectures do better than others. We don't quite understand why. But you'll see here that both one architecture that's based on state space model, in here Mamba 2, and one transformer do better than the two others, right? But this principle is somewhat, is robust to architecture choice. It's really about prediction in general. Okay, now another toy task, the last one I want to show you, addresses kind of like the elephant in the room, which is the fact that one assumption for this theory or this theorem to hold is that you need non-IID data. But of course the world, you need IID data, but of course the world is non-IID. Language is non-IID. All the sequence models are non-IID. Like these large language models are non-IID. So we've come up with a toy task to capture non-IID data and see if the same principles hold. The toy task goes as follows. We have a family of hidden Markov models in which we have ingredients, parts, such as the transition matrix, the emission matrix, all kinds of different things that we can sample from each family and come up with a model. And the job is to observe transitions from that hidden Markov model and predict the next token, right? When we pre-train a transformer to do this on a particular collection, and we hold out a few things that we've never showed the model, and that we ask in context if the model can generalize to unseen sort of hidden Markov models that come from this process. The idea here is that during training, you have seen all the components, but you have to learn to recombine them compositionally to predict well in context. And what we show here is if we skew training to include shorter and shorter sequences, but we control otherwise all the amount of data that's seen, that we generalize much better in terms of if we train on the frequential objectives, i.e. autoregressive objective, than if we just train on big sequences alone, right? And in this plot, what I'm showing here, I should unpack this, is that this is the distance between 0 here is the oracle, so given observations of transitions from a Markov model, and if you know which family it came from, how best can you infer which model it came from? If you haven't seen much, then the oracle is not good, right? So everything is close to chance here. But then as we go further here, the distance to 0 is how far away from the oracle you are. Now I'd like to point out that on the models that were skewed on shorter context length, you generalize much better, even in longer context lengths, than the model that was trained on full sequences, right? So again, there's a lot of confounders here, and like this is still work in progress, but it's consistent with the fact that if you give pressure to the model to jointly optimize different length of data sets, then you generalize better across the board, right? Okay, and there's reasons to believe that the way it does this is that the models that come out of in-context learning in these cases are much more compositional in nature. So I'll just flash a few other papers that look into this, and I'm happy to discuss about this a bit more if you want. Okay, so here's a summary here. I've shown you that parametric training, the training in weights of sequence models, actually can be seen as learning an optimizer T. Given a context, this optimizer T generates a model, non-parametrically, in activations. And this cumulative sequence prediction objective, which is unsupervised in general, is a good principle to get you to the point where you have these on-the-fly optimizers for in-context learning. Okay? So, is this useful for AI? Like, you know, that's a nice picture, but essentially I'm just telling you the stuff we do in LLMs works great, and this is, it doesn't tell us more beyond this. Well, there's a few avenues in which we're actively exploring. First of all is that you can use frequential coding length as an indicator of efficient data curricula, right? So I think using that component that we can compute is a good way to guide what type of data you want to show next in a model. Happy to talk a bit more about this. And the second is that given the point of view that sequence models are actually optimizers for in-context models, then you can try hybrid methods. In other words, you can say, if all that a transformer is doing is trying to arrange its activations to optimize a model in context, maybe you can find where in the transformer these activations are doing something that is akin to optimization. You can help it along with optimization methods, such as regression and so on and so forth. Right? So this is a line of work in collaboration with Jean Sacramento and Johannes, and actually Alex as well in the Google Paradigms of Intelligence team, where we are actively looking at methods that join both in-context and optimization to actually accelerate this principle of in-context learning. Okay. Okay, so let me close up here. I think I'm a little bit over. Yeah, okay. Sorry. So, take-home messages. Neural networks are special, right? I think there's something special. It's not an accident that our brains are made of neural networks, and artificial systems work best with neural networks because they're expressive in parametric and non-parametric ways. There's a unique relationships between weights and activations that's actually kind of not well understood, but I think it's quite powerful. And that evolution kind of gave us kind of clues. And this is principles that are architecture agnostic to a certain point. There's evidence in neuroscience that people are starting to look at this dual representation between weights and activation. This is an example of a paper that's currently out there. Second is that sequence prediction is special, right? It's general, it's self-supervised, and it could lead to these learning mechanisms in context that are quite expressive. Foundation models are all about that, right? Extracting nice statistical properties that can be repurposed to in-context learning on the fly. And the third is that context access is key. And this is where neuroscience can help us in AI, I think, because there's reason to believe that the brain has actually optimized this process for higher order sort of cognitive level. I think there's a lot of evidence, including Kayvon's talk here, that shows that plasticity drives a lot of learning on many areas of the brain. But if you think about cognition and memory and the role of all of the other brain areas that talk to each other with activity, then if you think about this as a big context machine, right, then I think there's a lot of interesting question with the type of learning that happens in the brain. And a key point is that the brain seems to do consolidation of in-context learn functions quite well. If you learn to play tennis, at first you need to concentrate. You need to load up the whole thing in your brain. And then at some point, it becomes second nature. You don't think about it, right? So there must be a process in which you take in-context models and you consolidate them in weights. And with that, I will thank everybody, and sorry for going over. Thank you for your attention.
Thanks, Guillaume. That was great. Unfortunately, we won't have time for questions. I would propose we keep to a hearty 15-minute schedule delay and meet back here in about 10 minutes to have our last keynote. And otherwise, now it's a break. Thanks.